Swayam Prabha. Digital India. Educated India.
Okay. Next, in continuation of pseudocode, we have another topic is random variable neighbourhood descent. So, RVND iterates through the list O in the random order regardless of whether the fitness g of x improves or not. After the call of the selected operators O I, RVND moves to the another operator O suffix I plus 1. If at least one operator improves fitness g of x, the list of operators O is again randomly reordered and all of the operators are called the new order. The algorithm ends when none of the operators improve fitness. So, the pseudocode is shown in the algorithm 3.17. This strategy can be beneficial of the optimization, is often getting stuck in the same local optima as it adds extra stochastically to the optimization. Next, the random pipe variable neighbourhood descent, that is RPVND, as the name suggests, is the combination of RVND and PVND. It goes through the operation list O in the random order, but if an improving operator is found, the algorithm repeats the operator and call until a non-improving call occurs. So, the algorithm ends with none of the operators improved fitness. So, the pseudocode is shown in the algorithm of a function RPND of x of O and do x new is x and then shuffle the list O for O 0 in O, do x new O of x, and while g of x new is less than g of x and x maps to x new, while g of x is less than g of x previous and return x. So, this is called as random pipe variable neighbourhood descent pseudocode. Next, meta heuristic. So, the meta heuristic are high level strategies that use the previously described algorithm. They systematically balance between the exploitation and the exploration optimization components. So, exploitation means to focus on the search in a local region by exploiting the information that a current goal solution is found in the region, while exploration means to generate diverse solution to explore the search space globally. So, the meta heuristic implemented in the proposed solver work on the similar basis. First step is to generate initial solution x using one of the construction strategies C from the section. Then the meta heuristic repeatedly call one of the local search strategies L from this section and the perturbation P from the 3.3. The difference between the particular meta heuristic is a way of the perturbation are handled. So, iterated local search is ILS, is the simplest out of the 3 meta heuristics. The pseudocode is in the algorithm 3.19 shows that the perturbation P is called the constant parameter K. Also note that the parameter P on line 8 is called the best known solution. So, x best instead of the last occurred solution x. So, the function is ILSCLOPK, where x to C of bracket x best of L of x O, do x is P of x best k and x is L of x comma O. If g of x is less than g of x best, while time of not reached and return x best. So, this is the iterated local search pseudocode. Next, best variable neighbourhood search is an extension to the ILS, where the perturbation parameter k is a variable. The pseudocode BVNS is given in the algorithm. The function expects 2 extra parameter k min and k max. So, the algorithm starts with the k set to k min, but it is incremented by 1 up to the maximal value of k max after every local search that does not improve the best known solution is x best. On the other hand, the local search finds a new best known solution. The parameter k is again assigned the value of k min. So, this is the what a pseudo code of a basic variable neighbourhood search. That is the function BVNS. Requirement is of parameter C, L, O, P, K min, K max. Then the inbuilt is K to K min, X to C of bracket, X best is L of x comma 0, do X P of x best comma K, X to L of x comma O, if G of x is less than G of x best. So, x best is to X and K is K min, else if K is less than K max and K to K plus 1 while timeout not reached and return to x best. Next, calibrated variable neighbourhood search. Sampling from a too large neighbourhood in perturbation P may result in long runs of the local search algorithm. Therefore, it might be desirable to increase the neighbourhood size only when the local search algorithm converges to the same optimum as the best iteration. So, the CVNS is the extension of BVNS, where the perturbation parameter k is a variable. The pseudocode of CVNS is shown in the algorithm 3.21. The function expects two extra parameter k min and k max. So, the only difference to BVNS is that the CVNS extends the condition on the line L11 with the expression x equal to x best and k is k less than max. Next, problem specific components. So, this section provides implementation detail about the problem specific solver components used in benchmarking experiments, namely the lower bound vector LB and the upper bound vector UB. The solution representation and the fitness function is g of x equal to p of x plus g bar of x. The function g of x consists of two parts, the penalty function p of x and the actual fitness function g bar of x. So, the purpose of the penalty function is score to infeasible solution of x, so that the optimizer can make steps from infeasible towards the feasible solution. So, additionally this section provides MILP formulates used in Groby optimizer. So, capacitated vehicle routing problem. Let us assume that we are given the distance C equal to Cij, the number of available vehicle k, the depot node D. The solution of CVRB is a set of variable phi equal to phi1, phi2 and so on phi k of the node V. It is a proposed solver, however, the solution must be defined in the form of one perturbation with a repetition. So, this can be done by x equal to d comma phi1, d phi2 and so on d phi k d. The CVRP instant class is initially based on the following formulation. So, A consists of 1 to n numbers tuple, D is 1, the lower bound is k plus 1, 1, 1, 1, upper bound k plus 1, 1, 1, g bar of x is summation I equal to 1 to m minus 1 c of xi comma xi plus 1 and p of x is m1 into summation of A negation D of 1 minus fa plus m2 of x1 not equal to d plus m2 xm not equal to d plus m3 of k minus fd minus 1. So, A is a set of available nodes, x suffix I is the ith node in the solution of x, node 1 is a depot 1. Therefore, the first elements of the upper and lower bound is up and lp are k plus 1. The m1, m2 and so on m3 are some large constant as described in the 3.12. All the nodes except the depot must be visited exactly once. So, this is expressed by the sum in the first term in the penalty function. So, second and third term ensures that the solution x starts and ends with the depot node. So, the last term enforces the feasible solution as exactly k2s. So, next Miller-Tucker-Gemlin formulation is a MILP. For the comparison with Guropi optimization, the Miller-Tucker-Gemlin formulation was used. The proposed following is minimum of double summation I in A, J in B, Cij, Xij, such that the summation I x in B of Xij 1, where J V negation D, and summation J in B Xij is 1 if I a negation D, summation I in B Jid is equal to K. So, the maximum summation J in B xdi is K, therefore, Yj minus Yi plus Q of 1 minus Xj is greater than or equal to Qj. Therefore, Xij in 0 comma 1 where Y in R. So, where Xij is a binary decision variable which represent whether sum of the roots goes through the edge I comma j. So, the real variable Yj represent the sum of the quantity demands Qi of the nodes that precedes the node j in the current tour plus the quantity demand Qj of the node j. So, the equation 32 and 33 represent the in degree and out degree constraint for all the nodes except the depot D, and equation 34 and 35 represent the in degree and out degree constraint depot of the equation 36. So, enforces the continuity of the tours while also ensuring that the quantity demands in each route does not exceed the capacity Q. Next, quadratic assignment problem. In the following text, let us assume we are given the flow matrix F equal to Fij in R n cross n tuple, and D is a matrix of Dij in R n cross n tuple. Solution of QAP is a permutation phi of the nodes A. This makes the formulation in the proposed solver quite straightforward, as we can directly map x to phi. The following formulation was used for benchmarking. The following formulation was used for the benchmarking experiment: A 1 to n, lower bound all are 1, upper bound 1, g bar of x equal to summation I equal to 1 to n, summation j equal to 1 to n fi j d of xi xj, p of x equal to m into summation alpha in A of 1 minus f alpha, where lower bound and upper bound are unit vectors and they are equal. The only penalizing of the feasible solution is the number of unused nodes in the solution x multiplied by some larger constant m. So, the fitness g bar of x is identical and the definition in the section 3.13. Now, MILP formulation is Zhou-Yuan linearization was used for the experiment of Guropi optimizer. Using the binary decision variables xij and the real variable yij, we obtain the following minimum of summation I equal to 1 to n, j equal to 1 to n of yij plus fij, fii djj xii, such that yij greater than or equal to lij into xij, yij greater than or equal to uij into xij minus uij plus summation k not equal to I, summation I not equal to j of fik dj L and xkl, where I and j varies from 1 to n and x equal to xij in product of n and yij in R. So, where x is a permutation matrix and Lij and Uij are the lower and upper bounds, and Lij is a minimum of summation k not equal to I and summation L not equal to j of fik into gjl into xkl, and Uij equal to maximum of summation k not equal to I, summation I not equal to j of fik into gjl into xkl. So, for detail the description of MILP derivation discusses. Next, non-permutation flow shop. Let us assume we are giving next non-permutation flow shop. Let us assume we are giving processing time matrices B equal to Bij belongs to R power m cross n of the non-permutation flow shop instant with m machines and n jobs. So, the solution of NPFS is m permutation of a product I of length n. The solution x is a vector pi 1, pi 2, pi m. The following formulation was used for benchmarking experiment. A is 1 to n, lower bound all are m, upper one all are m, c bar of x is c max, p of x mean m1 into summation a in a of m minus fa plus m2 into summation pi in x summation a in a of 1 minus fa pi. where LB and UB, where LB and UB are equal, are vectors with all elements equal to M. Cmax is the end time of the processing on the last emission. F suffix A pi is the frequency of node A in the permutation pi, and M1, M2 are some large constants. The first term of the penalty function P of x penalizes the solution if the frequency of any node A is not within the bounds M. The second term enforces that the solution x consists of permutations, not variation with repetitions. That is, each emission process each job exactly once. For the experiment, Guropi optimizer, the formulation introduced in the section was used. So, the MILP is defined the equation 14 and 19. Sudoku. Let us assume that we given the initial assignment A is Pik, where I to 1 to R. The solution to Sudoku is an assignment of the remaining free fields. The solution is a vector of x in j n square minus cardinality of A. In other words, the solution x contains the indices from j of all the free fields. The following formulation in the proposed solver framework was used for the bench marking experiments. A equal to j equal to 1 to n, lower bound n minus f1a comma n minus f2a and so on, n minus f1a, upper bound n minus f1a comma n minus f2a and so on, n minus f1a, g bar of x equal to 0 and p of x equal to summation b in b, summation I in j of 1 minus fi b. So, fi a is the frequency of the index I in the initial assignment A, B is the set of n rows, n column, and n square submatrix. The frequency FIB represents the number of occurrence of the index I in the block B. Note that Sudoku is not a typical optimization problem, but rather a constraint satisfaction problem. Therefore, the fitness function g bar of x equal to 0 and the overall fitness g of x consists solely of the penalty function p of x. This is understandable because we only care about the feasibility of the solution rather than their quality. MILP formulation for the experiment for Guropi, the 3 index binary variable was used. If we denote xijk assignment of the index k to find the field in row I and column j, we obtain the following ILP: minimum of the function, minimum 0, and then such that summation k minimum O such that summation k equal to 1 to n xijk equal to 1, where I comma j varies from 1 to n, and summation I equal to 1 to n xijk equal to 1, where j comma k varies from 1 to n, and summation j equal to 1 to n xijk equal to 1, then I comma k equal to 1 to n. So, cyclically you have to take it, and then summation j equal to m of q minus 1 plus 1 to mq, summation I equal to m into p minus 1 plus 1 to mp, xijk equal to 1, where k equal to 1 to n, pq varies from 1 to m, then xijk equal to 1 and xijk belongs to 0 comma 1 for all I comma j comma k in A and for all I comma j not in A. So, the equation 60 enforces that every field has to have assigned some value k. The constraint 61, 62, 63 ensures that each value k is in the every row, column and sub square matrix exactly once. Next, capacitated vehicle routing problem. So, the CVRP experiments were conducted on instances drawn from 2 different data sets. The small instances come from the data set proposed by Philippi Auguste in 1995. So, these instances consist of up to 100 nodes. The medium and large instances were taken from the data set proposed by Dorado, Uko et al., which provides the problem with up to 1001 nodes. The following solver configures was used on all CVRP instances. So, they are meta heuristic, BVNS, and k minimum is 4 and k maximum 8. Locus such is a PV and D. The construction is a greedy. perturbation is a double bridge. The operators are 2 opt, move 1, move 2, move 3, move 4, move 5, swap 1 and 1, swap 1 2, swap 2 2, swap 2 3, swap 2 4, swap 3 3, swap 3 4 and swap 4 4. So, these are all the operators we have to use. Now, the optimization result from the proposed solver and Guropi optimators are listed in the table. Note that the instance name consists of one letter followed by the number of nodes n and 2's k. The best known solutions for computation of the percentage difference were taken from CVR-PLIP. So, the result shows that the proposed solver is superior to Guropi optimizer in solving the capacitated vehicle routing problem in multiple aspects. So, the Guropi optimizer was able to find a feasible solution for only the 3 smallest problem and failed to obtain it on the medium and large instances in the given time span. On 2 out of 3 small instances, the final fitness was more than 10% larger than the optimum. On the other hand, the proposed solver was able to find the feasible solution for all the problems. Moreover, the average fitness g of x bar of the solution to the small instances was within 0.2% of the optimal solution and 1.5% of the medium instances are optima. So, this is a table with the CVRP optimized result. The row starting with the symbol star are instances with a known optimal solution, and this displays the gap BKS over time obtained by the proposed solver on 4 different problems. It also shows the average time of the last improving local search. It is apparent that on the large instance x suffix minus n 561 minus k 42 and x suffix hyphen n 1001 hyphen k 43, the solver was making improving local search steps until the very end of the allocated time and would have probably continue improving the fitness of a bigger timeout was set. On the other hand, we have a picture of the a minimization step for the 4 different instances of the gap BKS, and then the average of the last improvement of x suffix minus n 148 k 46 is suggested that optimizer was getting stuck before searching the timeout. This histogram shows that the 2 opt operator was the most improving operator from small to larger instances. So, you can notice that the slight increases in the move 1 and swap 1 bins on the instance, and x suffix minus n 1001 hyphen k 43, but the rest of the operators in both the histogram have very small similar distribution. Since the pipe variable neighbourhood descent selects the operator sequentially, so we cannot simply state that 2 opt is the most effective operator on CVRP, because the algorithm always starts with it. To prove this statement, more experiments over more instances and configuration are needed, which was not feasible because the time is limitations. So, this is the histogram that what we explained just now, and then we have to swap. Next, non-permutation flow shop. So, instances from data set proved by Ballada et al. Were used in the NPFS experiment. It contains a problem ranging from a very small instances 10 jobs on 5 missions to large instances 800 jobs on 60 missions. So, the data set is originally proposed for perturbation flow shop scheduling problem, which is almost the same problem as NPFS, with the only one difference that each mission must use the same which is almost the same problem as NPFS, with the only one difference that each mission must use the same permutation of jobs. So, the input of FSSP, that is a flow shop scheduling problem, is same as NPFS and therefore can be used for NPFS as well. So, the following solver configuration was used on all NPFS instances of meta heuristic ILS k equal to 3, local search BV and D, construction is a random replicate, perturbation is a random move of all, operator is exchange nodes, move all to 10, exchange first n nodes. So, the optimized results of the proposed solver and the Guropi optimizers are listed in the table. The instances names have the following format. So, VFR XS YYID, where XS is the number of jobs, YY is the number of mission, ID is the integer in range 1 to 10, as the VFR data set contains 10 different instances for every job, and mission number selection also required. So, the best known solution for computation of the percentage differences were taken from Liberaloso iterative beam algorithm, which are to our best knowledge the best known solution of to FSSB, even though these values are not NPFS solution, they can used as upper bound because every feasible solution of FSSB is feasible solution to NPFS as well. That is, the fitness of optimal solution of FSSB is larger or equal to NPFS on the same input. That is why VFR 20-15-1, the proposed solver was able to find even better solution and has a negative of gap BKS bar. So, this is the picture shows that NPFS optimization result for the solver problem better on NPFS than the Guropi optimization. The Guropi optimizer was able to find the feasible solution for only the small and medium problems and failed to even construct the model for the large instances because it ran out of the memory. So, the proposed solver was able to find a better solution on all the tested instances. So, this is the picture of the fitness minimization steps for 4 different instances, and the figure this displays the gap BKS over the time obtained by the proposed solver on 4 different problems, including the average time of a last improving local search called T bar. The displayed plot suggests that the solver was making improving local search steps until the timeout was reached and would have the probably continued improving the fitness if a bigger timeout was set, even though the slope seems to be very flat when approaching the timeout. So, the histogram shows that the most improving operator was exchange nodes. On the small instance, the other operator also played an important role, while on the large one they became less significant. The basic variable neighbourhood descent selects the operator sequentially so that the dominance of exchange nodes operate can be caused just by this. So, we empirically found out that the other available operators were significantly less efficient on this problem. So, in the terms of the time complexity and the number of improvement, therefore, only these 3 operators were used for the final experiment. So, this is the histogram where we demonstrated just now, and see that the exchange nodes varies from 0 to 8 lakh, and then the corresponding improved calls and standard deviation also explained. One is blue and other is standard deviation is a red color. Next, Sudoku. Sudoku instances used for the experiments were taken from the data set created by HUW Lloyd. There are 3 types of Sudoku instances. One is 9 cross S, 16 cross 16 and 25 cross 25. The names of the instances have the following format. The instance n cross n hyphen p hyphen id, where n is the size of the Sudoku and p is a percentage of the assigned fields. The following solvers configure was used in the all Sudoku experiment. So, the configuration is meta heuristic is BVNS and k minimum is 2 and k maximum 6, and local search is PV and D, construction is a greedy, perturbation is a double bridge, operator is move 1, 2 opt swap 1 1. So, from the result it is apparent that GUROP optimizer performed better on all Sudoku instances. Not only it found the optimal solution of the each instance, it only needed a couple of seconds to achieve that. The number of times in which the proposed solver was able to find the optimum is denoted by cardinality of opt. Is also equal to the number of time in which the feasible solution was found as the only feasible solution is optimal. So, the proposed solver was able to find optimum of all 9 cross 9 instances in all runs. The 16 cross 6 instances were optimally solved in only some cases, and 25 cross 25 instances were never solved. The reason for the poor result of the proposed solver might be the fact that heuristic algorithm generally do not aim to find the optimal solution. Another interesting observation is that while GUROP optimizer needed more time to solve the Sudoku with the lower assignments, percentage p, the proposed solver performed better when p was a lower. So, this is the result of proposed solver and GUROP optimizer, and instances also given, and this table represent the Sudoku optimized results. And figure 4.7 shows the fitness g of x over time obtained by the proposed solver on 4 different problems. On the 25 cross 25 instances, we can see that the proposed solver was making improving steps until reaching the timeout. On the 16 cross 16 instances, the average lost improvement t bar appears to be in the first half of the allocated time. So, this is the probably caused by the fact that some of the experiment reached the optimum prior to their timeout. So, the histogram shows that the most improving operator was move 1 but swap 1 2 opt also made a significant amount of the improving calls. We can see that this distribution does not shift from the between 9 cross 9 and 25 cross 25 instances. So, this operator histogram is also affected by the fact that PV and D selects the operators sequentially. Again, we empirically found out that the other available operators were less efficient, and therefore, only the three operators were used for the final experiments. So, this is a Sudoku fitness minimum step for 4 different instances, and this is a histogram of move 1 swap 1 2 opt. One is 9 cross 9, another is 25 cross 25. Next, based on the conclusion, the general purpose optimizer are convenient tools that can be applied to the wide classes of optimization problem with shared representation. Typical examples are integer programming solver like GUROP or constraint satisfaction solvers like CPLX. We proposed a representation formalism. Which allows to address a large group of problems whose solution can be represented using the dynamic permutation representation. Then we designated a neighbourhood oriented heuristic solver that exploits this representation. It adapts a multiple well established meta heuristic that can be used on virtually any combinatorial optimization problem and combines them into one powerful optimizer. So, we compared the solver to the commercial IP solver, GUROP optimizer on 4 problems: CVRP, QAP, NPFS and Sudoku. So, each problem was formulated using both the proposed solver framework and integer programming paradigm. So, the experimental results showed that the proposed solver implemented in C++ outperforms the GUROP optimizer on CVRP, QAP and NPFS problems in terms of scalability and solution quality given a fixed computational budget. However, it did not outperform GUROP on Sudoku. So, this might be caused by a poor choice of the proposed solver components, operators, perturbation, etc., or because of heuristic algorithm generally do not excel in finding the optimum solution, and the only feasible solution Sudoku is optimum. So, we compared the solver to the commercial IP solver GUROP optimizer on 4 problems: CVRP, QAP, NPFS and Sudoku. So, each problem was formulated using both the proposed solver framework and the integer programming paradigm. Concerning future work, we plan to extend the list of operators and perturbation. For example, NPFS has a very specific structure that was hard to exploit using the currently implemented neighborhoods. Additionally, other meta heuristic like taboo search and simulation annealing could be easily incorporated in the solver and might improve the performance on some problems. So, we perform the experiment with a fixed timeout by Guropi is the exact solver, and by definition it will find the better or equal solution than the proposed solver given unlimited amount of time. So, another interesting question is how much time it takes the Guropi optimizer to obtain such a solution on CVRP, QAP and NPFS problems. Therefore, we suggest experiments with a longer timeout should be made. So, the proposed solver is a primarily designed for COPS, and Sudoku experiment showed that the solver might not be suitable for solving CSPs. So, the tested optimization problem do not have many constraints. So, it is reasonable to carry out the experiment with a more constrained optimization problem. Example, capacitated vehicle routing with the time windows or flow shop scheduling with the resources constraints. So, these are all the references, you have to follow them, and so further you can understand. And also refer the paper meta heuristic algorithm for optimization problem sharing represented by Jan Hazard Rafa. So, it is taken from the journals. Now, these are all the glossary of best known solution for BKS, branch and bound for BNB, and basic variable neighbourhood descent is BVNT. These are all the acronym, and you have to use for the problem solving. And then these are all the further references you have to understand the problem. One is called it as Mathematics for Machine Learning, the Cambridge University, written by the Deisenroth and Faisal and Cheng Soon. Another book is Introduction to Applied Linear Algebra by Boyd and Vanderbergi, and it is published in Cambridge University Press. And Probability and Random Process published by Tata McGraw-Hill, publisher, and then written by T. Veerarajan, and Avrim Bloom and Job Ofcott, Foundation of Data Science, written by Ravindra Khanna, and another machine learning taken from the website, that Introduction to Machine Learning by Nishdeep and given by the IIT Kanpur. So, these are all the references, you have to do that. Further you can understand the beauty of mathematics for machine learning and mathematics for ML and AL, that is mathematics for machine learning and artificial intelligence. So, the unit wise learning outcome is unit 1, upon the successful completion of each unit, the learner will be able to understand the fundamental concept in linear algebra, and unit 2 is understand the concept of analytical geometry, apply the matrix decomposition concept in machine learning techniques. Unit 3 deals about that the outcome is analyze the concept of probability and distribution and study the concept of optimization in machine learning, and unit 4 is apply the principal component analysis for dimensionality reduction and apply linear regression technique for predictive analysis. And the course learning outcome is successful completion of this course, the learner will be able to understand the foundational concept and techniques of linear algebra, apply the linear algebra concept in approximation and matrix decomposition under the concept of dimension reduction and PCE. So, apply mathematical approach to solving problem in machine learning and data science, analyze the regression model with the hypothesis test and interprets the result, and develop the application using machine learning techniques. Thank you.